So in this video, I want to discuss the solution of the posted kind of challenge problem when we have the integral from 0 to 1 of the fourth root 1 minus x to the 4 dx. So I'm going to show the solution of this problem when I take just any p, and in this case, p can be any natural number. And so the problem that I posted as a challenge problem is going to be one particular case when p equals to 4. So if I want to find the value of this integral. And the idea of the solution that I'm going to present tonight is basically to represent this integral as a double integral. And the meaning of this single variable, single integral, is the area under this graph, under this function. So let's first try to graph this function and see how this function looks like. And then I'm going to show you how you can actually use double integral to relate this problem. So what I'm given here, my function y is equals to the p root of 1 minus x to the p. Hey, yeah, integral time. And in this case, let's find the graph of this function. And the graph of this function, what can I do? I need to raise both sides to the power of p and bring x to the left-hand side. So what I will get after this, I will get x to the p plus y to the p equals to 1. And then I want to graph this one in xy plane. So I have my xy plane. One graph, we know when p equals to 2, we will going to have just a circle. And it's going to be circle with radius 1. But the point is, if p is going to be, for example, equals to 4, then my graph approximately going to look something like this. So it's not going to be a circle. It's going to be kind of circlish square when you take the circle and bend it towards the corners of the square. Yeah. So this integral particular is just calculating the 1/4 of the area of this region. But if I want to relate this integral, the idea is I want to compute the area of the whole region. And what is the area of the whole region for this region in xy plane? And the area of the whole region, as we know from multivariable calculus, let's actually use it from here. So area is going to be equals to what? It's going to be equals to double integral over a scalar function, which in this case is going to be equals to 1. So we'll have the double integral over 1, because this is by definition, the double integral over 1 will give you the area of the region in xy plane. And here we'll have my dA, and I'm integrating over what? I want to integrate this over the region which is represented by all points inside. And this is exactly x to the p plus y to the p less or equal than 1. And what do I know? If I'm going to compute this integral, then value of this integral is going to be just 1/4 of the double integral of x to the p plus y to the p less or equal than 1 dA. Okay. And let's keep this one as our goal. So this was step 1 when we set up our integral. So right now what I want to do, I want to compute this double integral. Oh, you didn't see. Yeah. Okay, sorry. The integral that I brought over here. So let me put here lines that. So integrals that are which represented by area is going to be this integral. So this is area of D, when D is, in this case, is this region. Okay, so let's find the value of this integral. So the value of this integral, what I want to do, I have x to the p plus y to the p less or equals than 1 of 1 dA. Here I'm going to use a change of coordinates. An idea is when I'm giving some region that doesn't look as a circle, I want to take this region by change of coordinate, change this double integral over the integral over this circle. And how I'm going to do this? You can see if you will take this equation x to the p plus y to the p less or equals than 1, by change of coordinates, let's say I want to get the equation y squared, u squared plus v squared less or equals than 1. And what do I need to do if I want to get this equation? I need exactly to make my change of coordinates to be equals to u squared equals x to the p, and v squared equals y to the p. And let me remind you, in this case, what is going to be the form of this integral after we change, apply change of coordinates. I will have the double integral over the new region. So let's call this red region is going to be d prime. And d prime is, in other words, is going to be just u squared plus v squared less or equals than 1. So I will have this double integral of u squared plus v squared less or equals than 1. And here I will need to find my Jacobian, and I will get new area element dA1. So let's find our Jacobian. Jacobian of this one, first I need to solve this in terms of x. I will have that x equals u to 2 over p, and y going to be equals to v of 2 over p. So my Jacobian is exactly going to be represented in the following form. So Jacobian is going to be equals to x of u, x of v. It means like x partial u, x partial v, y partial u, y partial v. And you can exactly check that x of u is going to be equals 2 over p times u to the power 2 over p minus 1. Then x partial v is 0, and the same one, y partial u is 0, and y partial v is going to be 2 to the p of v 2 over p minus 1. So in this case, we can conclude that my Jacobian is equals to just the determinant of this matrix, and I will get 2 squared over p squared, u to the power of 2 over p minus 1, times v to the power of 2 over p minus 1. But the thing is, I need to take the absolute value of my Jacobian, so I will take absolute value. These guys are positive numbers, so it doesn't matter. So I will have absolute value here and absolute value here. So after I apply my change of coordinates, what I will get the integral, the double integral of u squared plus v squared less or equals than 1. This part is my constant, so I will have 2 squared over p squared, and here I have the double integral of u 2p minus 1 and v 2p minus 1 dA prime. Okay, let's separate this. So, and right now by using change of coordinates, I didn't simplify actually this integral into this one. And what I'm going to do, I'm going to find the exact value of this integral. And I'm going to make a claim. So let's just remember this picture. So we're computing the integral from 0 to 1 of p root of 1 minus x to the p dx. So I'm going to make the following claim. Let's keep it. And the claim is, if I will take that integral, I will take the double integral of u squared plus v squared less or equal than 1. And if I will take the absolute value of u to some power alpha times v absolute value of b, v to the absolute value of v to the power of beta, and my every element dA, where in this case, let's just remember my alpha and beta is going to be equals to, so my alpha, you can see, so my alpha is going to be equals to 2p minus 1, and my beta is also equals to 2p minus 1. So what I'm doing over here, I'm just generalizing this coefficient to be alpha and beta. gonna come around. Okay. I think it works. Oh, hi, black pen, red pen. And over here, I want to compute this integral. And my claim is that this integral is going to be actually equals to, and this fact is like really cool, the gamma function of alpha plus 1 over 2 times the gamma function of beta plus 1 over 2 over the gamma function of alpha plus 1 over 2 plus beta plus 1 over 2 plus 1. So what I will get? I'm going to prove this fact, like let's say in a couple of minutes, but let's plug it in my alpha in beta inside this formula and let's see what I'm going to get. And again, like I'm going to give you proof of this fact like in a second. So if you're going to plug in alpha in beta in this formula, and let's just write over here what is my alpha. Alpha is equals to 2 over p minus 1, and beta equals to 2p minus 1. So after we'll plug it in this inside this formula, 2 over p minus 1, I can see that 1 and 1 will get cancelled. And I will have 2 over p over 2. So what I will get just equals to gamma 1 over p. And you can check the same you will get for the second integral. You will get the gamma 1 over p. So, and on the bottom, you will have 1 over p plus 1 over p. So you will have gamma 1 plus 2 over p. Okay. And this is this integral is the result of computation, not of this integral, sorry. It's the result of computation of this integral. Yeah. And here we can see, I'm going to prove this in a second, but I got this integral by changing of coordinates of the double integral of this area of this region, because originally I want to compute the line integral from 0, 1 of p root, which is in this case just the area of this region. And I generalize this, I can compute the area of the whole region, which is given by this equation, and just divide by 4. So what I need to do, I can see during my change of variables process, I will have here 1 over 4, and here I have 2 to the square. So 4 and 2 squared will get cancelled. So, and I have an extra factor 1 over p squared. So I will have this gamma times 1, sorry, here, times 1 over p squared. So finally, my integral from 0 to 1 of p root 1 minus x to the p dx is going to be equals to. Here I'm going to use one property of the gamma function, and the property of the gamma function is gamma of x plus 1 equals to x gamma of x. But in my case, what I'm given? I'm given the gamma of 1 over p. And here I will move this 1 over p, 1 of the 1 over p, in front of this gamma. And another 1 over p, I will move in front of this gamma. And you can see that for this and for this gamma, in my final answer, I will just get the gamma 1 over p times 1 over p, just 1 over p plus 1. So we'll have gamma of p 1 over p plus 1. And since we have like two the same terms, it's going to be squared. And here I will have gamma of 1 over 2 over p. And voila, this is going to be the answer, desired answer for this integral. And I got this answer again from this fact. Let me use another colored chart. Oh, this one. I will got this answer from this fact, which I need again, like I want to prove it. And I got this by plugging in my alpha and beta, b exactly 2 over p minus 1 and 2p over p1 minus 1. Okay, so yeah, no, it's not like the job is not ever done, because the most coolest is the most complicated part is actually to show this result, to show like this integral is equals to this gamma function. And then you can start to play around, because you can plug in different alpha and find different integrals. So you will get a family of really nice and good integrals. Okay, so let's actually prove this fact. So what I'm going to do, so my first step, here I'm integrating over a circle, over inside of my circle. And this is my u, this is my v. So, but using one of the theorem definitions of double integral, I can integrate this iteratively. Or in other words, I can rewrite this integral in the following form. I can write this integral as first the double integral of, here my u changes from -1 to 1. So we'll have the double integral of -1 to 1. And here I will have my du. And I want to separate my function to move this function outside of my inside integral. So what I will get u alpha, and my second integral is going to be what? By the topic from, by using definitions of double integrals, we know that outside boundaries of my function is going to be numbers, which in this case numbers, but inside boundaries is going to be functions. And since I choose my order to be du, dv, then if you want to find the bounds for my functions, you just need to draw like this red arrow in positive v direction, and you can see it first will intersect this function, and then it will intersect this function. So in other words, what I will get that my u squared is going to be less or equal than 1 minus v squared. And the reason is why, because it will go from negative square root of 1 minus v squared to positive square root of 1 minus v squared. Okay, and here what I will have my v beta. And let's just separate these integrals. I have this no, not use parentheses. Okay. Let's just, I'm going to come back to the integral for a second, and I want to take a look on the integral of inside. But when I'm going to take a look at this integral, what is the meaning of this one? For each u, for example, when u equals to 0, no, one second. Okay, so what I'm trying to do, let's write down this integral. So I have the integral of inside of u squared less or equals than 1 minus v squared, and I have v to the power of beta dv. And here I can see, oh no, there's a mistake. Sorry, it's v squared minus u squared, because I have my v as a function in terms of u, because the equation of this one is going to be minus 1 minus u squared. Okay, yeah. Then you can see for any value of u, when you go and plug it in over here, you will get that your v is going to be bounded by this function. And so inside this integral, there is no value of u. So what you can do, you can introduce the new variable r, which is going to be equals to 1 minus u squared. And when you're going to introduce this variable r, let's just rewrite my integrals in terms of r. So r in this case is going to be a parameter. So we'll have the integral of u squared minus or equals than r squared of v to the power of beta dv. And again, like I'm evaluating this integral when I split this integral into two iterated integrals. And right now I'm considering this integrals inside, and I want to do some operations inside. And what I got so far, I got like this integral, and right now it's like annoying. I know I'm going to use again change of variables. But how I'm going to use a change of variables? I want to make this integral, because right now this integral over some interval from minus r to r, but I want to make this integral to be from -1 to 1. And how I can make this? I can introduce a new variable w Or in other words, I can divide both sides by r squared. So I will have u squared over r squared. So you can see if you will make, if I will make w equals to u over r, then I will write this integral as a line integral over v squared less or equals than 1. And then here I need to change my v in dv. Oh, sorry, it's not, again, mistake. It's v. Yeah, it's not u, it's v. Because this is my r, so I divide v divided by r squared. Yeah, it's v. And then from here I have that my v equals rw. So dv is equals rw dw. So first, instead of v, I'm going to plug it in rw to the power of beta. And dv I will be expanded as r dw. So this integral is going to be equals to, I will split my r, so we'll have integral from v squared less or equals than 1 of r beta plus 1. I get rid of absolute value because my r is over here is positive. And I will have w to the beta dw. Okay, I got this integral. Since this r depends on u, and I'm looking for the integral in terms of w, hi, then I can factor this r outside of this integral. So I need more space. Let's see. Yeah, let's just rewrite this. So I will have r beta plus 1 as the v squared over v squared over r squared less or equal to 1 beta, and I will have the integral from v squared less or equals than 1 of v beta dv. So again, what I'm doing, I'm computing the integral inside. The only last part that I need to do, I need to compute this integral. So let's compute this integral separately. So what I will have over here, I will have the integral of w squared less or equals than 1 of w to the power of beta dw. This, I'm integrating the integral from -1 to 1. So in this case, I can just write this as a 2 times the integral from 0 to 1. When w changes from 0 to 1, absolute value is positive, so we'll have w beta dw. And this equals to just 2w of beta plus 1 over beta plus 1 from 0 to 1. And you can check it's actually equals to 2 over beta plus 1. Wrong blackboard. So this integral is equals to just 2 over beta plus 1. So the whole thing is going to be equals 2 times r beta plus 1. And what I did over here, I found the value of exactly of this integral. So this integral inside is going to be equal to 2 r beta plus 1 over beta plus 1. Okay, so let's erase what I'm not using here anymore. So I'm not using this part. And for the people who just joined, what I'm doing over here, I'm trying to compute this integral, the integral from 0 to 1, pi root of 1 minus x to the p, like d, okay, no, doesn't matter, dx, and this is going to be just 1/4 of this area. And I make this claim, so right now I'm proving this claim. So I can rewrite this integral then as an integral from -1 to 1 of u alpha, and this thing is going to be equal to r beta plus 1 over beta plus 1. So one thing, remember, when we did the computation for this integral, we make that our substitution r equals to 1 square root of 1 minus u squared. Yes? So what I will have 2 times, but this is square root will just equals to 1/2. So I will get 1 minus u squared. When I will take my 1/2, my half will become beta plus 1 over 2. So we'll have beta plus 1 over 2. And also I need to divide by 1 over beta plus 1. So I can put it over here. So it's going to be over 1 beta plus 1. And this is my d. And we're almost done. So right now, the only thing which is left over here, okay, so I have this 2 over here, and this 2 goes here. Okay, so right now I want to relate this integral. And here I'm going to do a couple of steps. So first of all, what I want to, okay, so let me just show the formulas that I want to use. The formulas that I want to use one of the properties of the gamma function. And what is the property of the gamma function that I want to use? I want to show that I will know that if I have the integral from 0 to 1 of x u minus 1 times 1 minus x v minus 1 dx, then this integral is going to be equals to, sorry, I wrote this. Let's say this way, gamma of u over gamma of v divided by gamma of u plus v is equals to the integral from 0 to 1 of x u minus 1 minus x v minus 1 dx. So right now what I want to do with this integral, I want to transform this integral into this form. So let me show how I should do this. The first thing, I want to have this v minus 1, but here I don't have v minus 1. So what can I do? I can add 2, yes, and subtract 2. And then when I'm going to factor this, I will have beta plus 3 over 2 minus 2 over 2. But 2 over 2 will just give me minus 1. And here, I've got the first thing. So over here, my desired v is going to be beta plus 3 over 2. Okay, what to do with this alpha? This alpha is a little bit tricky. So first of all, you can see we have u squared here, but we don't have u squared here. Before I'm going to make u squared, I'm going to separate this u into 2 components. I will have u alpha minus 1. But before I had u alpha, so what I want to do, I want to multiply this by u. And but before that, sorry, I have integral from minus 1 to 1. And before even here, my function here is even when it's alpha. So first step, I need to change this integral from 0 to 1, and I will multiply by another 2. And then I can get rid of this absolute value because my u, so this is u. My u will be positive and it changes from 0 to 1. And then I can separate this into u alpha minus 1 times u. Okay. I hope it was clear. And the next step, what can I do over here? If I want to create the u squared, I will just make this u squared. But what I need to do with my power, I need to divide my power by 2. So I have alpha minus 1 divided by 2. Okay. And the last step, what do we need to do? So here I have 2 times 2. And one of the properties of differentials that we know is the differential of du squared equals to 2u du. I believe I did one of the video when I prove this property. And so it means I can take this 2, this u, and I can change my differential, so I can go backwards. So in this case, what I will erase my u over here, will erase my 2 over here. So I will have du squared. And if I'm going to do, again, like change of variables, then I will set just my x equals to u squared. according to this formula, according to this form, I can change every u squared to be equals to x. So we have x, x, and x. Or in other words, when you had here over here u squared, by just taking x equals to u squared, you can get the desired form. Okay, thank you, Kusi. Hi. Thank you, Spike. Yeah, I'm trying to be my video accessible. I hope this is accessible. So I changed everything to x. And what I get over here, right now I can apply the property of this gamma function. So I have integral from 0 to 1 for x. So, no, not yet, sorry. Here, I want to have u minus 1. So what I'm going to do over here, I'm going to add 1. I need to add 2 and subtract 2 on the top. So you will have alpha plus 1. These two will get cancelled. And then minus 2 over 2, I will have exactly minus 1. So right now, my u over here is equals to alpha plus 1 over 2. And finally, what I got over here? I got that integral equals to 2 beta plus 1. And right now, I have u x minus 1 minus x v minus 1. And this is equals to gamma of u. But u in this case is going to be alpha plus 1 over 2 times gamma of v beta plus 3 over 2 and divided by gamma u plus v. So here we'll have gamma alpha plus 1 over 2 plus beta plus 3 over 2. Okay. And you can see that it's almost identical to our claim that this double integral over a circle, a unit circle of u alpha v to the beta dA equals to this gamma function. And here's small tricks that I need to do before. So if I want to get identical answer, you need to separate 3 as 1 plus 2. So we'll have beta plus 1 plus 1. And here we use the property of the gamma functions that we discussed before, that gamma of x plus 1 equals x gamma of x. So in this case, I can see that my x in this case, beta plus 1 over 2. Yes, second. 2 beta plus 1. So first I want to change this one. If I will do the same over here, I will have beta plus 1 over here. So my bottom part check. And 2 over beta. Yeah, everything is right. So right now this is my x. So what I'm going to do over here, I will put this beta plus 1 over 2 in front. Why? Because I can move from this expression to this expression by erasing 1. So I'm erasing 1 over here. But I need to put this x in front of my integral. And in front of the integral, I will have exactly beta plus 1 over 2. So beta plus 1 will cancel. 2 and 2 will cancel. And finally, we're going to get this integral. So what we just did over here, we proved this claim. The video is going to be accessible, like I think maybe like in 10 hours or like when YouTube is going to process, and you can see the whole proof. And by proving this identity, I show like 10-15 minutes ago. I believe I already erased. Yeah, I already erased. I show the value of this integral from 0 to 1 of p root of 1 minus x to the p. And for people who just joined, I can just erase this and show you the final answer to this integral. So this integral is going to be equals to just gamma 1 plus 1 over p squared over the gamma function of 1 plus 2 over p. And this was the value of this integral. Deep fried for a sec. Okay. So that's it basically. And I was super surprised when I computed like this. I didn't compute this integral. I was trying to compute this integral, and then I found the article when they computed this integral. But they computed this integral in more general notation. And what they were doing is they were computing the volume of n-dimensional ball, but of volume of n-dimensional ellipsoid, and this was super cool. So the formal derivation was more complicated. But if you will take just simpler case when n equals to 2, which is this ball in xy plane, then we're gonna obtain this nice result. And as a homework practice and homework, plug it in p equals to 2, and get that this integral is going to be equals to area of a circle is pi of the unit circle. So this is going to be equals to pi over 4. Yeah. Okay, so I decided to do live session because I'm so lazy to record this, to edit this. So I just decided to do live session and solve this integral live. So I hope you enjoyed this video. If you're not subscribed to my channel, please subscribe. And tomorrow, the day after tomorrow, I'm going to post challenge number 2. And my goal, what I want to do, I want to post some videos, some challenges, where I'm going to introduce some new concepts. And I'm going to show you how you can use this concept to solve some really cool problems. Okay, so thank you for watching, and bye-bye.